Today I'm gonna teach you how to solve Rubik's Cube. You know, there are so many formulas out there, very complicated stuff, turn left, turn right, all of that. No, screw that. I found a very easy way to do that in 3 easy steps. Easy peasy lemon squeezy. Super easy to do. If you have Rubik's Cube at your home, definitely pause this video, bring it like to the screen of the computer. We're gonna solve it together. Okay, ready? Okay, step number 1. You need to solve any of the colors. Let's say red. Okay, let's say this red. Okay, and then second step, you need to learn filmmaking, because when you do filmmaking, you can do something like this. Now, oh, hold on. That's actually it. Sorry. Lecture number 23. Let's go. I hope you guys enjoyed the merge sort. That's actually one of the examples of divide and conquer. Remember, like back in the day, we were talking about decrease and conquer algorithms, right? So when you decrease the problem, okay, but either by 1 or by some variable or by 2, by a factor of 2 or by some other factor, and then you solve like one portion of the problem, and then you kind of guess what the solution to the original problem would be. Okay, so that was decrease and conquer. Now, merge sort though is one of the problems which belongs to the category of divide and conquer. Not decrease and conquer, but divide and conquer. Okay, and like that's a little bit different. So that's something what I want to show you guys today as well. Let's come to the slides. Okay. So what is the general plan for divide and conquer algorithms? Divide, not decrease, but divide. They're similar, but not the same. Okay, so step number 1, problem is divided into several subproblems of the same type. Okay, so it's divided into several subproblems of the same type. The problem is not increased in size, but it's divided. Okay, so that's why it's divide and conquer. Okay, of the same type, ideally of the equal size. Okay, step number 2, the subproblems are solved typically recursively. Okay, and then number 3, if necessary, the solutions to the subproblems are combined to get a solution to the original problem. Okay, so if I was to draw a diagram, here's what it would look like. So let's pick this color. Okay, so let's say that is the original problem of size n. Okay, and then we, let's say, divide it into 2 parts. Okay, and then after that we get 2 subproblems. So if you remember the diagram I was drawing last time for decrease and conquer, right? You probably remember that there was only one piece like this. Here though we have 2 pieces. What does that mean? That means we don't decrease the size of the problem. The size of the problem is the same. We just divide the problem into 2, for example, subproblems, ideal of the same size. And then let's say we divide each one of them into 2 and recursively keep doing the same thing, right? But anyway, at some point, let's say if we decide to stop here, we solve these 2 subproblems of size, let's say n over 2, and then we combine them back. Okay, so yeah, so we get, let's say there's the solution to the first subproblem. That is the solution to the second subproblem. Okay, and then can't really draw here. But anyway, so let's say that's the solution to the original problem. Yeah, sorry, that's small. Okay. Okay. Yeah. Yeah, so again, I have a problem of size n, then I divide them into two pieces of n over 2 sizes, and then I combine, I solve them separately, I find the solution to each one of them, and then combine the solutions somehow such that, and I get the solution to the original problem. If you remember from the merge sort, what happens is that you divide the problem, you divide the entire array into two pieces, right? Then each one of those into two pieces, into two, into two, into two, until you get an array of 2 elements, and then you sort that. So you sort an array of 2 elements only. And then you combine 2 arrays of 2 elements, so you sort 4 numbers, right? And then you combine, 2 arrays of 4 elements, and so on. Yeah, so that will be divide and conquer, okay, instead of decrease and conquer. Okay, so if you ask what is the difference between divide and conquer algorithms and decrease and conquer algorithms, the difference is the following. In decrease and conquer, we decrease the size of the problem, solve that, and then we're trying to understand what the relationship between the solution of the smaller subproblem and the bigger subproblem. Okay, and based on that, we logically derive the solution to the bigger subproblem. In divide and conquer, you split the problem into let's say two pieces or 3 pieces or millions of pieces, and then you solve each one of them. So in decrease and conquer, you solve only one of them, only one subproblem, and that's enough because you know the relationship. In divide and conquer, you solve each one of them, and then you kind of merge them together, and then you get the solution to the original problem. Hope it makes sense. Okay, that's the idea. For example, okay, let's consider a problem of computing the sum of n elements. Okay, or f of n numbers. Okay, so let's say I have n0, n1, n2, n3, and up until n. Okay, so there are n numbers. Okay, so if n is greater than 1, we can divide the problem into 2 instances of the same problem, compute the sum of n over 2 numbers, then the sum of the second n over 2 numbers, okay, and add those together. Okay, and that will be a perfect example of divide and conquer algorithm. Okay, again, not decrease and conquer, but divide and conquer algorithm. Hope it makes sense. Okay. An instance of size n can be divided into b subproblems or sub-instances of size, ideally n over b, okay? Of size n over b, with a of them needed to be solved. Okay, so not sure if you remember, but at the beginning of the class we were talking about recurrence relationships. It's basically when you have a function and you describe that function, the value of the function, not through concrete numbers, but through the value of the same function, but on the smaller argument. Okay, hold on a second. Yeah. So it usually looks like this: t of n is equal to a times t of n over b plus f of n. So that is a perfect example of recurrence, and that's actually where recurrence is used. For instance, to solve almost all the problems in divide and conquer algorithms. Okay, so T of n represents the amount of work, or like the work, or well, yeah, I guess the solution. Yeah, the final number, the solution. Well, no, I think it's more about the work. So T of n represents the amount of work you need to do to solve the original problem size n. That's equal to, right, a times T of n over b. So if we divide the original problem n into b chunks of n over b size, in this case you have T times n over b, and let's say you need to solve a of them. So it's not necessarily, so a may be different from b. For example, if we consider the problem when we divided the problem into two pieces, like when we're summing up the numbers, okay? So we just have, let's say, 1,000 numbers, divide them into two parts, 500 numbers on the left, 500 numbers on the right, sum them up, and then just sum the numbers, the two other numbers you left with, okay? In this case, in how many chunks do we divide the problem? Two, right? Now, how many sub-problems do we have after one division? In this case, two. So again, how many chunks do we divide it into? Two. So b would be equal to 2. And how many sub-problems do we need to solve? Or like how many times do we need to solve, like I guess sub-problems? That would be a, which is also 2. And you just keep in mind that a and b may not be the same thing. It's possible that you divide, for example, into 3 chunks, but you solve in, for example, only 1 or only 2. So it's very important. Okay, and now f of n is basically the amount of work which needs to be done in order to split a problem into sub-problems. And then like once those sub-problems are finished, once they're done, like to get everything together. Okay, so in our case, for example, what does it take to split the numbers into, like an array of 1,000 numbers into like 2 groups? I don't know, big O of 1, right? It's very, very small. Now, and what does it take once you solve both sub-problems, once you found 2 numbers, how long does it take to add them all up, right? Just to add a number to number. It's also big O of 1, okay? So it's just like a constant. Okay, so that's why like f of n sometimes it's most likely will be a constant number, the big O of 1. Most likely you will not have to worry about that at all. Anyway, yeah, so that's the recurrence. There are a couple of ways of solving that. One of the ways, probably the simplest one to solve, is called the master's theorem. Master's theorem, okay? Master's theorem is the way to solve a recurrence, and it's like kind of as simple as plugging in some numbers into the formula, okay? You just need to know that formula, but for the final exam, since it will be open book, open note, you can easily Google that, or you just can kind of like look it up in the notes, okay? So master's theorem looks like this. If f of n, which is this guy over here, right? If f of n is in big theta, insert to special character, come on, yeah, if it's in big theta of n to the d, okay. So if f of n belongs to big theta of n to the d, okay, where d greater than 0 is greater than or equal to 0, okay, then, okay, and here's the thing. So then T of n can be solved like this. There are 3 cases. Number 1, if okay, a is less than b to the d, okay, then T of n is in big theta of n to the d, okay. Second case, if a is equal to b to the d, okay, if a is equal to b to the d, then T of n is in big theta of n to the d, and then times log n. So like n to the power of d, and then log n is outside of the power. So it's basically log, well, let's spell it this way. Log n times n to the d. Okay. Now, so it's less than. Now here's we have equal n, equal to b to the d, and the only thing which is left is if n is what? Less than, equal to, greater than b. Sorry, if a is greater than b to the d, okay, then t of n is in big theta of log, n to the power of so it's n to the power of log a base b, like this. Okay, so it's n to the power of log a base b. Yeah, okay. So here's the idea. When you see the recurrence like this, all you have to do, you need to find a, b, and then look at fn, right? So if fn is n to something, n to the 0th power, for example, n to the 1st power, n to the 2nd power, n to the 3rd power, so n to some constant power, okay? If that's the case, in this case, Master's theorem can be applicable. It can be applied, you can find the solution to the recurrence. Okay, so how do you do that? You just need to like solve, you need to understand where does it belong to. Is it like this? Is it this? Is it this? Okay, so you plug in the numbers there, understand which one, and you basically have the solution. Okay. Okay, for example, let's say the recurrence, we're not talking about specific algorithm, but let's say the recurrence, it looks like t of n is equal to 2 times t of n over 2 plus 1. Okay, so in this case, a is equal to 2, b is equal to 2, f of n is equal to n to the 0th power, okay, which is equal to 1. Perfect. Which means d is equal to 0, right? Okay, cool. So the question, which case is that, right? So what would that be? That would bring us to the moment when a is greater than b to the d. Okay, a is greater than b to the d, which is this. Okay, and in this case, we can say that t of n is in big theta of n to the power of log a base b, okay, which is the same thing as, so what's our a? Our a is 2. What's our b? Our b is 2, okay. So what's log 2 on the base of 2? Okay, so what power do you need to raise 2 into to get 2? So that's 1, right? So log 2 base 2 is 1. So n to the 1st power, okay, which brings us to big theta of n, okay? And that's the solution, you found it. Okay, awesome. Hope it makes sense. Hope it helps. Now, moving on to quick sort. Quick sort. That's something which we're going to start today, and I think we'll finish up next time. Okay, I know. I think on Thursday, actually, I'll also give you some resources to study online. But quick sort is actually an amazing algorithm. Yeah. Okay, cool. So here's how it works. Quick sort. Okay, again, remember, it's not divide and conquer. It's divide and conquer, not decrease and conquer. So here's how it works. Maybe it's actually, maybe that's what we'll do today. I'll give you a general explanation of how it works, and then I will ask you to read the book. And I'll give you some like also online tutorials. Yeah, online tutorials. And I'll ask you to submit the notes on Monday. Yeah. By the way, guys, so today is almost the last lecture. You are doing a very good job. Just push through. Okay, I really hope the coronavirus is not impacting you. And I really hope that we'll get back to normal soon. I really hope so. Anyway. So Okay, so let's say you have an array like this, okay, and the idea behind the quick sort, yeah, let's say it's called quick sort. Okay, quick sort. So by the way, not sure, honestly not sure why it's called quick. I guess when it was just created, it was immediately called quick. But ironically, as for now, quicksort is the quickest sort in practice. So the quickest sort ever, as for now, the quickest way to sort an algorithm, you know, like we have bubble sort, merge sort, insertion sort, selection sort. The quickest way to sort that is this, is the quick sort, ironically. Okay. Anyway, so let's say we have an array of this size. Okay, and the idea is this: we're going to select so-called pivot. Okay, I'm not sure if you know the etymology of the word pivot. I remember when I first heard that, like, and I started looking in the dictionary, it was difficult to understand what specifically it means, and I didn't know English that much. And I actually found that pivot means a lot of different things in a lot of different contexts. For example, when people create startups in the companies, to pivot means to change the direction of the company. For example, I don't know, the company was developing, let's say, I don't know, let's say there is Uber, right? And let's say at some point, like maybe nowadays, Uber is not like important that anymore because nobody drives. And let's say Uber decides that, hey, we can actually make much more money if we develop self-driving cars, okay? And then they change direction of the business. So that's called to pivot. So pivot would be like the moment of change. I guess maybe it has kind of a similar meaning here. So pivot would be, yeah. Anyway, so in this context, in quicksort, pivot is the most important element in the array. Okay, so you select the most important element in the array, either randomly or you select it to be the first element, right? Maybe this guy over here, maybe this guy over here. Okay, it maybe like randomly somehow. It doesn't really matter. Anyway, so you select the pivot first, and the pivot is going to be the most important element in the array, around which everything is going to take place. Okay, so for example, let's say I have an array of numbers. Let's say it's 20, 10, 20, 30, 5, 6, 1, 3, 4. Okay, and let's say I randomly, or like let's say I always select the first element to be the pivot or the second element to be the pivot. I somehow need to understand, like, determine for myself. It doesn't really matter how you do that, just like, but you have to do it somehow. So usually it's either the first element or the last element or the random element. Okay, let's say I select 10 to be the pivot. Okay, and now the idea is this. This array is going to be, after the first iteration, this array is going to be transformed in a way such that we're going to have 10, and then on the right from 10 will only be the elements which are greater than 10. For example, 20, 30. And on the left from 10 are going to be the elements which are less than 10. Not necessarily sorted. Okay, so for example, they can be like 4, 3, 1, 6, 5, 6. Okay, so that's like kind of my array after the first iteration. Okay, so anyway, I have 10. Okay, I have 10. Now everything on the right is greater than 10, not necessarily sorted. I do not know that yet. On the left from 10, I have all the numbers, all the elements which are less than 10. Okay, and then what I do again, so like I divided this problem into two sub-problems, this one over here and this one over here. Okay, and what kind of conclusion can I reach? Okay, for example, in this particular case, if after so-called partitioning the array, right, it's called partitioning because we create two partitions, we create two parts. Partition is like a technical term. After doing this, when I know that I have 10 in my array, all the elements on the left from 10 are less than 10, and all elements on the right from 10 are greater than 10, what do I know? Kind of what conclusion can I make at that point? The conclusion I can make is this. No matter what I have on the left and on the right, no matter what kind of numbers and no matter what order they're in, the 10 is in the exact position where it should be after the entire array is sorted, right? Because like if you change this to 1, 3, 4, 5, 6, okay, the 10 is still in the same position. If you change like 20, 30 to 30, 20, or if they were, like, for example, 15 and 20, in this case you changed, like you shuffle that, you shuffle these guys over here, you shuffle these guys over there, but 10 will always be 10. So 10 is kind of in its final position, it's fixed, that's it. Okay, yeah, that's the idea behind the quick sort. That's kind of the simplest mechanism. Select the pivot, select a random number, just like do something. It's called partition, right? Place it in the right place. All the elements on the left should be less than that. On the elements on the right should be greater than that. Okay. Then you have this elements, and then what do since it is divide and conquer? Okay, so you split the problem into two subproblems. You need to solve each one of them separately. Okay, kind of similar to the merge sort. Okay, so again, the next problem would be so I split them into two subproblems. Okay, now I need to solve this one and this one separately. Again, I do exactly the same thing. So I select the pivot. Let's say, again, I want it to be the first number always. Okay, and then I select it to be 4. Okay, then on the right hand side, I'm going to have the elements greater than 4. So let's say 5 and 6. And then here I'm going to have like 3 and 1. Okay, over here I select 20 to be the pivot. On the left, I need to have everything less than 20, which is nothing, and on the right, I need to have everything greater than 20. Okay, so I'm pretty much done with this part of the array. Okay, now, so the problem here is that, yeah, so 4 is in its final position as well. Okay, now I split this into two parts again, and I solve them again. So 3, 1. Okay, and what kind of problems do I have? I have this one over here. And I have this one over here. I have 3, 1 and 5, 6. So now I need to solve them. 3, 1 and 5, 6. So what do? I select the pivot, which is like 3, for example, right? And everything on the left from 3 should be less than 3, which is only 1. I don't have any other numbers there. And everything on the right from 3 should be greater than 3, which is nothing. Same thing for 5, 6. Okay, so I select the pivot. Let's say it's 5. Then after like some iteration, right? So you should read the code like to see actually how exactly it happens, how I and J move, all that. It's pretty cool. Yeah, so it's like 5 to be the pivot, and then after the partitioning, everything on the left from 5, which is nothing, right? I don't have any elements, should be less than that, and everything on the right from 5, which is 6, should be greater than that. Okay, and then basically that is my that's my answer, right? That's my answer. So like 1, 3, right? Then 4, 5, 6, then 10, 20, 30. Yep. And then you just combine them all together, and then yeah, that's what I have. 1, 3, 4, 5, 6, 10, 20, 30. So now it's sorted. That's the idea behind it. Okay, hope it makes sense. Now let's talk about the time efficiency. Okay, I definitely want you to read the code and definitely want you to understand how it works, how it functions. But if we take a look at the time efficiency, okay, time efficiency. We're going to have. So best case scenario, so it really depends on how the array is structured. If the array is already sorted, then like you just partition, that's it, okay? If the array is sorted. So if the array is sorted, that's going to be C best, right, of n. How much work are we going to perform? So it's going to be 2 times C best of n over 2 plus n, okay? So again, what happens is that we divide the problem of size n into two subproblems, right? So that's why it's 2 times C best, right, of n over 2, okay? And then when we're done, we just need to merge them all together, and it takes n to do that, okay? because like you have n over 2 on the left, n over 2 on the right, you just need to put them back together, and then that takes n, or n minus 1 technically, of the time. Okay, so if you solve this using the master theorem, it's going to be C best of n is going to be n log n. So n log base 2 of n, okay? N log n. So it's pretty much similar to all other sorts. As of now, I hope you remember, but yeah, it's actually, I'll be asking it on the exam as well. All the problems, all the sorting algorithms we've seen so far, they have n log n. Bubble sort has n squared. This one has n log n. And then if you take a look at C average, we're going to have 1.3 n log n. Yeah, so that's why it's the best. Take a look at what the case and the worst case scenario. Okay, I'll see you guys next time.